Okay. So we are still not really ready to start doing Haskell. We'll have to go through a little bit more category theory. I will introduce a little bit of Haskell code today, and it will be actually sort of like an advanced code, but it won't be a lot. We need to build up a little bit so that we can introduce Haskell, building it up on category theory rather than explaining the syntax and then saying, oh, by the way, this is what a product is, or this is what it is categorically. Okay. So last time Brendan started talking about lambda calculus, and I want to pick it up and continue. So he introduced the so-called untyped lambda calculus, which is the original version of lambda calculus. And he said that this is a very powerful thing. And indeed, it's an extremely powerful language. It's so simple, right? It just defines everything is a function, right? What can you do with a function? Well, you can apply it to an argument. What's the argument? What's another function? What does it return? It returns another function. Everything is a function, right? You can create new functions using the lambda abstraction. Okay. You can then do the beta reduction to evaluate something. So we have evaluation rules as well. So using just these things, you can actually start writing programs amazingly. And it turns out that you can write any program that can be executed by a Turing machine. It's called Turing completeness. What's a Turing machine? Probably most of you know, but it's just like a very abstract computer that has an infinite paper tape, and it can print stuff on this tape, maybe numbers, let's say, and then can read from this tape. And it has some state and can move the tape left or right or not, So it has a very basic set of instructions, compared to modern processors. This is totally trivial thing. The problem with both untyped lambda calculus and Turing machines is nobody would want to write programs for these things. Okay, this is not for humans. Maybe this is good for Alonzo Church. I mean, I think he was actually doing this stuff with pen and paper. He was very good at it. But for most of us, this is not possible. Okay, what is the main problem with this? The main problem is that in lambda calculus, everything is a function, right? Therefore, you can apply anything to anything. There is no error reporting. Okay? Any program you write is correct. Correct in the sense that the compiler will not, or the machine will not complain about it. It will just execute it. Maybe it will get stuck. Maybe it will go forever. Who knows? But if it doesn't produce the result that you wanted, there will be no help. Okay? You'll have to imagine debugging a lambda calculus program, even the simplest one. Maybe the simplest one, apply a boolean to true and see what happens. Okay, something like that. But anything more complicated makes no sense. Nevertheless, from the theoretical point of view, this is a great thing. And Church came up with these Church encoding, so he could encode in lambda calculus. He can encode things like booleans first, right? And then as functions, and numbers, okay, or Church numbers, Church numerals. So he can do arithmetic, addition, subtraction, all this stuff. Well, it's Turing complete, so you can actually write, Tetris game or something like that in lambda calculus. Not that anybody tried doing this. So how would you come about improving this language so that it's more human readable? You would say, well, instead of using these church numerals that are like horrible beasts, you know, why don't we just add natural numbers to it? Say, okay, we'll extend lambda calculus with natural numbers. Booleans, maybe, you know, maybe even rational numbers, or maybe even, you know, integers, strings, characters, right? So you just keep adding this stuff, and then the question is, well, if I have integers in untyped lambda calculus, you could take an integer and say, because it's a function, you can act with an integer on some other function. You know, it's like apply it to if, you know, if is a function too, right? Well, okay, does it make sense? Kind of doesn't, right? I mean, if you are designing a language, you would say, well, this is probably an error, right? So you would say, okay, here's a new rule. You cannot apply an integer to anything. Okay, so now you are breaking this beautiful picture in which everything can be applied to everything and every program is correct. Now you have programs that are incorrect. And in fact, when you start building this, you are saying, okay, so I have functions in this program, but the function can only this particular function can only work on integers, and this other function works on, you know, booleans, and it returns integers or booleans, and so on. So you will end up with a system in which functions are typed, right? So you have functions that act between particular types and nothing else. So suddenly, not every function is composable with another function. This is what we started with in lambda calculus. Everything was composable with everything, right? Because you can pass the result of one thing to another thing because it's all functions. They are passing functions to functions that accept functions. Here, you know, if something produces an integer, you can only compose it with a function that takes integers as input, right? So what does this remind you? It reminds you of a category suddenly, right? Because in a category, it's the same thing. Like in a general category, it's true that you cannot compose any two morphisms, right? You got this, right? The morphisms that you can compose have to be composable. Composable means the type, the return type of one, or the target of one, is the source for the other. Okay? So this way, first of all, you get what is called a simply typed lambda calculus, in which arguments to functions have type. Okay? So there is like some algebra of types, ways of creating new types from old types. There are some basic types and so on. You know, there is syntax for building types and so on. And every function returns something of a particular type. And then composition is only possible if these types match. And if you try to write a program in which these types don't match, it's not a valid expression in typed or simply typed lambda calculus. And suddenly, you know, you can write a compiler which will complain about your program, and this will help you writing correct programs. Okay? So we suddenly get, and we get a category out of it. So this is this famous category that we talked about all the time, right? The category of types and functions, right? And the main thing is that not every two pair of functions can be composed. They have to match end to end. Okay? That's what makes it a category. So now a little bit of Haskell. Okay? So like if you want to define a variable in Haskell, you have to, well, you don't have to tell the compiler what type it is. If you don't, then the compiler will provide one for you. Okay, so this is like the rule. It's like if you don't specify the type, the compiler will figure it out for you. There's there's some kind of type inference engine built into Haskell. But for us, at least in the beginning, maybe later we'll relax the rules a little bit. For us, it really makes sense if we stick to providing types for everything. So like if you define a variable called x, you will define it as saying, let's say, it's of type int. Okay? That means x is a variable of type int. And if you want to, I mean, if you write something like this in a program, the compiler will complain, well, you have declared the type, sorry, double colon, okay, so I'll come back to it. The compiler will complain that you have provided a type signature. So this is called a type signature. It just tells you doesn't tell you about the value of x. It just tells you about what type it is. The other part is you have to define what value it is. So you could say, okay, it's an integer, so I can say its value is, let's say, 42. Okay? And this is now a valid program in Haskell. Don't type it into GHCI, because GHCI, like this is like two separate lines, and in GHCI it's like you usually do one line at a time, and the compiler immediately complains after the first line. There's a way of inputting multiple lines, but it's like if you put it into a file and you compile it, then it will work. It will compile. Well, it probably complain that you don't have main. That's another problem. But we're building slowly, right? So int is one of the types. Okay, what's an int? It's a 60. Well, probably in most implementations it will be a 64-bit integer. Okay, so it's not really an integer in the sense of mathematics, right? It's an integer modulo 2 billion or something like that, right? It will wrap around if you keep adding stuff. If you want to calculate, things like factorial of 100 or 1,000 or something like this, if it doesn't take forever, then you would probably use a different type. You would use integer. So integer is the bigger type. Integer actually is a full-blown integer. It can go to infinity. So why don't people use integer instead of int? Performance. That's all about performance, because int translates directly into machine word. Okay, most processors nowadays have 64-bit integers built into their instruction set and into their register and memory and so on. So they can operate on this stuff so fast that you won't even notice, right? Whereas if you have integer, it's implemented probably some kind of tree or something. It has to be extended, It's like if you grow it, then you will have to allocate more memory in it. It will spread several words in memory, more and more, right? What are the types? Well, there is a bool type. Okay, the difference between integer and bool, for instance, is integer and int. These are built-in types, so the compiler knows about them and will optimize the stuff. Then there are other types that are just defined in the library. Bool is defined in the library because it's a combination of simpler types. Okay, so from these built-in types, you can build other types, and we'll be talking about this when we talk about universal constructions. How you build more complex types from simpler types. Okay. Then there is this little problem with function types. Okay, so we've seen that. So if we have objects A and B, right, then there is this home set from A to B of morphisms. Okay, so what does this correspond to in Haskell? Well, it would correspond to a set of functions from A to B. But I say set because in category theory, this is a home set. This is really a set. Now, if I want to write it in Haskell, I would write something like this. I would say f is of the type A to B. So this is more or less the same thing, except that now I'm confused, right? Because, okay, these are morphisms. So these are arrows between objects. So this is an object, let's say int, right? This is an object bool. And this is a function that goes from int to bool, say is even. Okay? Now if I say, what is the type of is even? Wait a moment, this is a morphism. This is not an object in my category. Types are objects, remember? Okay? So there is a little problem here that we will solve later when we talk about exponential objects. In set, this is not a problem because this is a member of a set of the home set. Right? So a function in set is a member of a home set, and a home set is a set, and the set is an object in set. So no problem, right? But in an arbitrary category, this is not necessarily true. So in an arbitrary category, we can't do this. And there are some special categories called Cartesian closed categories in which there is an object for every home set. There is a special object that represents this home set in some special way. So I'm talking about this. This will be explained later. Okay. Okay. So, why double colon? Because there was a decision made in the beginning of Haskell that lists are more important than type definitions. Like, because we would write it as a single colon in math, but single colon was reserved for cons of a list because Lisp was very popular back then, you know, and in Lisp everything is a list. So they thought, okay, we have to. Now there are some new more modern languages like Idris or Agda. They use single colon. They went back on this, and you know, this was sort of a mistake. But it's not a big problem. Yeah, question?
Just want to make a comment for those trying to use VHCI. You can separate the type declaration from the definition with a semicolon.
With a semicolon, that's right. Yeah, I forget that semicolon is still possible in Haskell. Nobody uses it, right? Nobody uses semicolons, and you can even put them in braces, right? Like C++. You can, yeah. Yes, yeah. But most people don't do this. Haskell is like sensitive to white space in general. Like if you don't want it to be sensitive to white space, then you have to use separators. Otherwise, you write things one line at a time, and they have to be aligned. So the blocks are just aligned. Instead of using braces to create blocks, you just align them, you indent them, right? Okay. So now I could say, okay, so you know what a category is for these types and functions, and it's called Hask. And I would be lying a little bit, you know. It's like if there are people, I don't know, are there people in the audience who would catch me on this lie, or people who are watching the video will say, no. First of all, there is no category Hask, and then he's not talking about partial functions. So let me talk about partial functions a little bit, okay? So there is one big problem with this stuff. It arises because a function, there is nothing preventing a function from calling itself. Okay? And in untyped lambda calculus, that was perfectly okay. There is this y combinator that calls itself, makes even function call itself with itself, and so on. You can't do this in typed lambda calculus, but you can still call a function within a function, right? Call the same function within the definition of a function. That's called recursion, right? So you can recursively descend. And this is the way you implement like these traditional examples that people use, okay, factorial or Fibonacci numbers. Like everybody loves and hates these examples. But they illustrate the fact, okay? They illustrate that, like a factorial of n is equal n minus 1 times factorial, or n times factorial n minus 1, right? So it calls itself. It will eventually stop because there is also the special case for 0, right? If it's 0, then just return 1, right? But what happens with recursion is that if a function can call itself, or there can be multiple functions calling each other in a circle, they can go on forever, okay? Like if I didn't put this special case in the definition of factorial, it would never terminate, right? It would just like subtract 1, okay, let me call it myself with n minus 1. Okay, what do I do? Well, I call myself with n minus 2, then n minus 3, n minus 4, and if you do this with integer, right, which is infinite precision, you go forever. Okay, so you might think, okay, so maybe we can maybe we should ban recursive functions. Okay, well, no, that's too drastic, because then you can't even implement your favorite Fibonacci numbers or factorial. Okay, so no, bad idea. Well, maybe there is something called well-founded recursion. Well, you can actually even the compiler could prove that this finishes, right? With the case of factorial, there is like decreasing number, and is constantly decreasing, and eventually you will hit 0, right? So there is a proof that it terminates. There are other functions that also, like Fibonacci also does the same thing. So they terminate. Okay, so there are languages that total languages. That's called total language. Like part of Idris is total. Idris has like special parts, total part and non-total part, right? Haskell doesn't. So you could say, well, okay, if it's possible, then maybe we should stick to these functions that we can prove that they terminate. The thing is that there's this theorem, that you cannot really decide, upfront. Somebody gives you a function and asks you, does this function terminate or not? There is no algorithm to tell, okay? Like if you come up with an algorithm, you say, this is my algorithm, it will tell. I can find a function on which this will fail, okay? This is sort of like a diagonal argument. It's like every time you give me a function, I will find a counterexample, right? By looking at the diagonal somewhere. Okay. So there is a theorem also, another one, that if you want to have a Turing complete language, so every program in this language every program that can be executed by a Turing machine has to be also executed in this language, then you cannot ban this infinite recursion. So in fact, you have to allow partial functions. A partial function is a function that when it terminates, it will give you a result. But there's no guarantee that it will terminate. Okay? So for some arguments, it will just go on forever. Yes?
Some questions over there.
There are questions?
I was just wondering, how important is Turing completeness? Like, are there practical examples of programs that we can't, like, that we can't prove terminate that we want to run another business?
So I'll repeat the question. Yes. So how important is Turing completeness, and can I give examples of things that? So as I said, you know, Idris, for instance, it starts as a language that's Turing complete, right? But then, well, for instance, there are programs that are extremely useful that run on servers. Like, for instance, a server. Server should not terminate, right? So there is a special way of dealing with it in Idris, right? You can say, you know, it's like if this goes forever, you know, for too long a time, I give it some gas that it can burn, right? And if it runs out of gas, it will stop and say, sorry, I cannot go on forever. Yes?
Well, it is true that you cannot give an algorithm for any arbitrary function, but when we are writing programs, we are just writing particular functions. So actually, the programmer itself can provide the proof of termination or well-foundedness. So, for example, the language I'm working with, Concat proof assistant, allow you to actually provide these proofs.
Right.
So can like this be instrumented? The language can be instrumented with this to actually allow.
Right. So yeah. So the question is, like, there are some languages in which even though the compiler cannot prove for an arbitrary program whether it terminates or not, there are some languages in which the programmer can write a proof, and this proof is being treated as like a data type, you know, that can be passed to a function. And here's the proof that you terminate, you know, and so on. And the theorem prover, like Coq, right, can actually check the proof. Okay, the proof is correct. Yeah. So that's a possibility, but of course, it's not very practical in general. Like, if you are doing some theorem proving, yes, that's a great thing, right? And definitely not in Haskell, where proofs are not first order citizens. Okay? So this is why we are going to live with partial functions, and there are even some partial functions in the standard library. You know, there is a function head that takes a list and returns its head, first element of the list, right? What does this head do when the list is empty? It throws an exception, terminates the program, okay? So it's not a complete function. It's not a total function, right? Okay. So let's write some Haskell code to show you that that Haskell is a category modulo these problems with non-terminations. Okay, so we'll be from now on ignoring this problem. Okay, it's like in programming, this is like a standard procedure: ignore problems, right? So we'll be true to this motto. So if it's a category, right, what do we need? We need identity and composition, right? So how do you compose functions in Haskell? So you see how I write a function declaration, right? So this is a function from A to B. Now, composition takes two functions and produces a third function. Okay, so what would be, let's say if I call it compose. Compose. What type is it as a function? So it takes a function, well, it takes two functions, right? And produces a third function. So let's say I'll draw the diagram. So the first function goes from A to B, then the second goes from B to C, and it produces a function that goes from from A to C. So let's call this F, G, and this will be called G after F. In math, this is how you would write it, right? Now I want to write this in Haskell. So the result should be a type of a function from A to C. OK, that's easy. A to C. I'll put it in parentheses, although it's not strictly necessary, right? Here, I need a function from, so in the opposite order, G after F, I will put G first, OK? So a function from B to C, right? And the second function is from A to B, OK? If this order confuses you, sorry. Can't do anything about this, right? So compose would be a function that has this signature. It takes two functions. So this is notation for a pair, right, in Haskell. Pair of functions. This function from B to C, function from A to B, and produces a function from A to C. OK? So that's just the syntax. Now, if you write it, the compiler will complain, of course, that well, you didn't provide the implementation, just the type signature. OK? So compose. OK? It takes a pair of arguments. So there are two ways. I mean, I could write it as a bunch of lambda, 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 because it has like two function arguments, and then it produces a function that has a third argument, right? I'm just going to write it as compose fg. So this is this. Remember the syntactic sugar for lambdas. Instead of writing something as a lambda, you can put the arguments on the left-hand side. Sort of pattern match. And the compiler will look at it and will say, maybe I should do G and F. OK? OK. Right? So the compiler will see G is this, F is this. These are the types. OK. This is equal to, and I will erase this. So I have to return a function from A to C. I will write this as a lambda. OK, when I write lambda on the blackboard, I will just use the Greek letter lambda. OK, you translate it to backslash when you're writing your code, right? So lambda, which takes an argument of type A, I'll call it x. OK, x is of type A. The compiler knows that it's of type A because it looks at it and say, oh, OK. And it has to return something of type C. Who returns something of type C? G does. OK? So definitely G. It will return something of type C, but it will only return it if I give it something of type B. Where do I get something from of type B? Well, F returns something of type B. OK, so I'm going to act on F, but F returns a B only if I give it something of type A. Do I have something of type A? X. Excellent. OK? So here's the implementation. And it will work. OK? Now, the actual implementation in Haskell, first of all, doesn't call it compose. It calls it dot. Because it's so often used that they want, it's like Morse code, you know. The most common letter is E, and it's just a dot. OK? Who knows Morse code here? Nobody. OK. So dot is a function that goes from B, C. And here's a little trick. OK? I'll explain in a moment. So two tricks. One is that if you want to call your function dot or period, right, then in this kind of, so it will become an infix. Like if you use a symbol rather than letters and numbers, okay, it will treat it as an infix thing. And if you want to put an infix and use it just like a function, you have to put it in parentheses. So dot in parentheses is this, and there's no. And the other, so several tricks here, okay? Several tricks. First of all, instead of doing a function that takes a pair of arguments, this is called currying in Haskell. A function of multiple arguments usually is not written as a function taking tuples of arguments. It's written a function that takes one argument at a time. So it takes the first argument and then returns a function like this. This function takes this argument and returns a function like this, right? The final pair of parentheses is not necessary because the arrow binds to the right. Okay, so this is just like every Haskell programmer knows this and they don't. You can put the parentheses, and I often put the parentheses because that's much more symmetric way of seeing this, right? And then if we wanted to define it like this, right, then I would treat it as an infix, and I would say g dot f infix between the two arguments. So here it takes two arguments. Here the dot is between two arguments, right? And I could even take this x and put it on the left side to do syntactic sugar and just say gfx, right? And this is how it's defined in the Haskell library. Okay. Now, I'll be cheating all the time, so get used to it. What am I cheating? What are these A, B, and C? Okay. What types are they? This is an int, bool. I can substitute any type here, right? Which means this function is called a polymorphic function. It works for any A, B, and C. Okay. And I told you that names of types start with a capital letter. Did I tell you that? If not, that's true. Names of types start with capital letters. These are lowercase letters. If the compiler sees a lowercase, something that starts with a lowercase letter, in type declaration, the position where it expects a type, it will automatically assume that this is a type variable. Okay? So A, B, and C here are type variables. They are not, so you can substitute any type for them, right? So this could be an int, then this will be an int too. This can be a bool, this could be a double, you know, and so on. So in any situation, the compiler will figure out what types you actually meant, but this is a very general formula, and we'll use it. All right? Yes?
What then is the type of dot? So how can you talk about types of things which are parameterized by types?
Okay, yeah. This is a polymorphic function. So it's possible to write it in a more explicit form by putting for all here, for all dot here, okay? When I put for all dot, then it means I'm actually using polymorphic lambda calculus, okay? And we'll talk about polymorphic lambda calculus later next week, okay? And the fact that I was able to write it and you understand this, yes?
Do you need to say what you're quantifying? Like, do you need to say for all A, B, C, or can you just say for all?
No, you're right. I have to specify for all A, B, C. Yes, dot. Sorry. Yeah. So I just want to stress one thing, that if I was teaching you C++, then something like this, I would maybe be able to show you at the end of the course, or if it's like a 2-semester course, because in most languages, first of all, polymorphism is very hard to express. In C++, this would be a template metaprogramming construct. Okay? That's one thing. The other thing, higher order functions, which is functions that take functions as arguments and return functions as results, are like really you know, it's like C++ didn't have lambdas till like, I don't know, 5 years ago or so. Java didn't have lambdas. Okay, they just discovered, oh, this is, people use lambda calculus. We never heard of I don't know. Maybe I'm exaggerating, right? Nobody was asking for it, so they didn't implement it, right? But now people are asking for it more and more, and they have to implement this in every single language. Okay, so now for something completely different. Oh, question.
I had a comment about that question. It's confusing. Just ignore it. Type of a type is a set, which is not.
Type of a type is a set, was he saying, and of course in Agda or Coq, that's what it's called, right? A type of a type in Haskell actually also has a name. It's the star, right? Yeah, it's called a kind.
I see.
Yeah. Okay, so now let's talk about something completely different, namely functors. Okay, functors. What should I erase? I'm gonna erase this because this is like all of Haskell for today. Okay, small portions. So the philosophy of category theory was we are more interested in mappings between things than in things themselves, right? And we showed you how this works with sets, for instance, and some other bunch of categories. Yeah, you're not supposed to look inside the dot, okay? And then we went ahead and talked about categories, saying, well, inside a category, you have objects and you have arrows. So this is kind of, you know, not really nice. We should not be talking about the internals of categories, or at least try to come up with a language in which we don't have to talk about internals of categories. So if we don't want to talk about the internals of categories, then we have to talk about mappings between categories, right? So what's a mapping between two categories? A mapping between two categories, well, it should map objects, presumably to objects, right? I mean, you don't want to map objects to arrows and vice versa. So the simplest thing would be to let's map objects to objects and arrows to arrows. But we want these mappings to also preserve the structure of a category. So a functor is a structure preserving, so this is the slogan, structure preserving mapping between categories that's defined for objects and arrows. And now I have to explain what it means to preserve the structure. So what is the structure of category? The structure of category is defined by how these dots are connected, right? So it's defined by composition and identity, right? This is how we define the category. So a functor that preserves structure better preserve these things, right? So if we have a functor f between two categories, it will be, first of all, a mapping on objects. So f acting on some object A. So A is an object, how did we write it? Obj of C, right? A is an object in C. Then FA will be an object in some other category D. So this is a morphism. Okay, let me not use the word morphism yet, but this is a category C, and this is the category D, right? And this is the functor F. And I will write it as dots now, okay? Or I can write them as blobs that have arrows inside. Okay? So for the time being, when we are defining this stuff, we can peek underneath and see what's inside a category, because we are defining mappings of categories. So we'll peek inside. We'll see that there are dots and arrows. Okay? So f of a, and we usually don't put parentheses because in Haskell we don't. So we'll just not. F acting on A. Functor acting on object A, which is an object of C, produces an object of D. So for every object in the source category, there will be some object in the target category. Okay? Now how should it map arrows? So if this is A and this is B, this will be FA, this will be FB. So if this is an arrow from A to B, let's call it F, it better map it to an arrow between FA and FB. You see, it makes sense, right? Because if it preserves the structure, like if these things are connected by a morphism, then the image should also be connected by morphism. So if we want to see the structure of C in D, we have to map arrows in parallel with object. So we will call this FF, F acting on F. Okay? So we have a mapping of objects, and we have a mapping of functions. Morphisms, right? So FF, single colon, yeah, is a mapping from FA to FB, as long as F is a mapping from A to B. Okay? And now it has to, I'm running out of time. Now it has to preserve composition, right? So if I compose arrows here, so there's some G here, right? C. You see, I can compose these two guys here, right? So this is G after F. I can compose these things too, because look, they are composable. The end of this one is FB, right? This is called FB, and this is FC. FB is the end of this one, but it's the beginning of this one, because in the way how we arrange things, they are composable. So I can compose them here as well. So I can say this is FG after FF. Okay? So I want the composition here to be translated into composition here. Because now I have a functor that acts on arrows, so I can take this arrow, G after F, also, and say, okay, this is F acting on G after F. Okay? So I can compose these two guys here, get one arrow, this one, or I can take this arrow, transport it here, and I get this arrow. They better be the same. Okay? Because if they are not the same, then I'm not preserving the structure. So preserving the structures means that they are the same. So what I mean is F of G dot F is the same as F G dot F F. Okay? And finally, identity, right? So what happens to identity? Identity is like, here's an object A. This is identity on A. A gets mapped into FA. What should this be mapped to? It should be mapped to an identity on FA. That means what preservation of structure is. So F acting on ID A is the same as ID, and these are right. And on FA. Okay, so this identity is in the left category. This identity is in the right category. But I can move them between categories using the functor. Right? So these two things guarantee that the structure is preserved. And because composition is preserved, then if there are any laws here, for instance, the unit law and the associativity law, they are beautifully transformed into here, right? So all the laws are preserved. Everything is preserved. So a functor maps these categories, preserving their structure. So this is a much more powerful thing than what we were using in set. We are using functions. We are thinking of functions. And functions sort of preserve structure, you know, because they map dots to dots. But dots don't really have nice structure. Well, you know, it's like, but here we have structure. We have arrows between these dots, right? So if an arrow goes from A to B, it's different than an arrow going from B to A. It's like there are different shapes that you can construct in the source category. And these shapes will be transported very nicely to another category by a functor. So a functor takes shapes in one category and transforms them into shapes in another category. It could shrink them because these things are functions, so they can like map multiple things into one. So you can take, you know, a beautiful shape with 100 dots and arrows, and you can shrink it down to a single object in the second category if you want to, right? It's a fine functor too. But in general, you know, they kind of preserve the shape. We'll see examples of preserving shapes and shrinking them in many different ways, right? But this is what was meant when we were talking about preserving shapes and finding one shape inside another, projecting a shape. You know, it's like a morphism, take shape of type, you know, A, and find it in some object of type B. This is really a much better picture than what we had with sets. So next time you think about morphisms and shapes, think about functors and categories, okay? Because there is much more structure in a category than there is in a set. And all this language about shapes and finding shapes, mapping shapes from one category to another, and generalized objects of shape A, and so on, they start making much more sense if your model in your head is that the source is actually a category and the arrow is a functor. Okay? And finally, maybe the last thought here. The last thought is, okay, so we have categories and we have functors between these categories. Okay? Usually when we have things going between things, you know, we would like them to form some kind of structure too, right? What do we call this structure? A category. Can we build a category in which objects themselves are categories and arrows between them are functors? Okay? And I don't know if anybody would protest if I say that yes, modulo size issues, right? It's like there are too many of them, right? But since we were, like from the very beginning, we were shoving this under the carpet and saying, well, we have a category of sets. Well, the sets of all sets. Objects are like the set of objects, there is the set of all sets, and nobody protested, then nobody will protest here, right? So, yeah, there is this category called cat. And in this category, categories, small categories, are objects, and functors are morphisms. And if you want to convince yourself, figure out how you can compose two functors, okay? And what is an identity functor? And we'll talk about this maybe next time. Thank you.